Good morning, chemists out there. How are you doing today? This is Sean Byrne coming with you with another lesson, actually a review of free response questions for AP Chemistry. I got to tell you, I'm still riding high from our conversation with Dr. Frances Arnold yesterday, Nobel Prize laureate from 2018. So if you haven't had a chance to watch that, I highly suggest you stop and go back and watch that right now, or take a look at it later on today, because Dr. Arnold had some amazing things to say, some really funny stories, and a lot of really good advice for all of us as we're moving forward in our preparation for AP Chemistry and really for further education. So take a look back at that in the feed when you have a second, because I think you'll really enjoy it. Today is Wednesday, April 29th. Remember that all of this week, we are doing reviews of free response questions. So there's not going to be any new content per se. We're going to take whole free response questions and give you some time to complete them on your own, and then go through our solutions and some tips and tricks for you as you're going through them. Any questions that you have regarding exams, you're still going to want to look back at apstudents.org/exams 2020. There's a list of things on the right there that are helpful for you if you have questions about any of those things. Remember that our date is approaching quickly, May 14th, Thursday, May 14th. Here in Chicago, we're going to take our test at 1 p.m., but around the world, whatever time correlates with Greenwich Mean Time of 6 p.m., we're all taking the test at exactly the same time. So correlate your time in your time zone to this time and date. Second reminder that the format of the exam will be two different questions, right? The first question, which is 60% of the exam weight, you will have 25 minutes to read and respond. So our assumption is that this will be a little bit longer question. And so in today's lesson, what I'm going to try to do is give you one question that's sort of modeled on what I would expect a question one to look like. So it would take a little bit longer. There are multiple parts to it. And then the second question that you will have on your AP exam is a little bit shorter, 15 minutes to read and respond, and then 5 minutes to upload it. So remember, all of this is focused on the skills that are listed here on the right-hand side of the screen. It's worth pointing out that Mr. Faribault and I have no idea what's going to be on the test. So we're not teaching knowing what those questions specifically will be like that you're going to get. There's a whole different team of people that are working on that. So what we're doing is teaching you as much good chemistry as we can, looking back at previous free response questions to give you a model of those and some of our how we would like to see some responses. Today, I have a couple of student responses, similar to what Mr. Faribault had on Monday. So you can kind of look at what some students did, what some of them did really well, where some of them got tripped up, and make some decisions to make sure that you don't make those same mistakes with your format or with your test in a couple of weeks. Okay, so the first question that I'm going to throw at you, I would encourage you to stop, take a screenshot, or just pause the video here, get out a sheet of paper, a calculator, a pen, a pencil, maybe a couple of different colors of pen just to keep yourself organized, and see if you can solve this. This problem has 4 parts on this screen, and then there's a second screen. In my mind, this seems to model what we will have as a 25-minute question, because there are multiple parts to it. So I'd encourage you to, like I said, take a screenshot of what's happening here. There's 4 parts, A, B, C, D here. And then the second part, or the next page of the questions, has you looking at a graph. And then don't forget part F down there at the bottom to answer a question about the higher concentration. Which species has a higher concentration? So I'm going to give you a second here to pause, do some solving of your own, and then come back to me when you have what you think is your good solution. Okay, great. I'm going to assume now that you have already done some of your own work on this problem. And I'm going to go through some of the ways that I would solve it, certainly keeping in mind what the scoring guidelines are. This is an official AP or released AP free response question from a number of years ago. We can look at what some students did and what the scoring committee said would be an acceptable response to this question. So the first thing is to look at, to write the net ionic equation between, between the reaction between KC6H7O2 and HCl. So anytime that I am answering a question like this, and when I'm talking to my students about it, I encourage them to write out the complete molecular equation. So this is not a scoring requirement. This is not a part of what you would necessarily be expected to write down. But in terms of your thinking about how this would, this reaction might proceed, I think that this is an important thinking step to for your own process in coming to a solution. And so what I would hope you'd be able to recognize is that this is a double replacement reaction. So the potassium and the hydrogen are basically switching chemicals, that they are trading partners. There's lots of different analogies out there for what a double replacement reaction would look like. And then from this molecular equation, what we can do is go to a complete ionic equation. So again, this is just a thinking step. This isn't the final answer by any stretch of the imagination. But what we would notice here, and this is a key part of the understanding, is that this acid that is formed over here, sorbic acid, I believe, is a weak acid. And because it's a weak acid, this is kind of what's driving the reaction and what we would not expect to be dissociated or ionized here. We would not expect the hydrogen and the sorbate to be separated. And so because this is going to be our ultimate product, it's going to drive and kind of help us define what all the spectator ions are in the rest of the equation. And so for me, starting with the complete molecular equation, then going to the complete ionic equation helps me to identify what's the one thing that's going to drive this reaction, what's the product that will help me then identify what my reactants need to be to get to that product, or identify what my spectator ions are. And so I'm going to notice that one of my spectator ions is chloride. And because chloride appears on both sides of the equation in exactly the same form, I would drop it out of the equation. It's a spectator. It's sitting in the solution, watching everything else have all the fun, watching everything else react. And so it is not involved directly in the reaction. Potassium similarly appears in the same form as a potassium ion on both the reactant and product side. And so we can eliminate that from the equation. And that gives us an ultimate net ionic equation of our two ions reacting to make our sorbic acid over here. And that would be the acceptable net ionic equation for the reaction between our two compounds. Now, some of you are able to look at the problem just as it is and able to see this net ionic equation in your head. Many of you are not able to do that, and that's okay. You're not expected to jump right from the problem that's here directly to this net ionic equation. So what I'm trying to do here is either to show you what you might write down in your test booklet, you might write down on a piece of paper, or maybe just the thinking that would go through in your brain to say, okay, of all of the ions that are here, what is the thing that we could be making, we could make as a product? Potassium chloride is a very soluble salt. Typically anything with chloride in it is going to be soluble. Anything that potassium salts are going to be very soluble as well. And so the idea that potassium chloride would be making some sort of a precipitate would not be expected. And so then we look at this and say, oh, this is a weak acid. It's not on our list of 6 strong acids. And so it makes sense that this would drive that reaction forward. Okay, so there's part A. Then we're going to use this equation to answer some questions about in part B. The problem tells us that we have a titration that with a total of 29.95 milliliters of 1.25 molar HCl. I'm a visual thinker. This is something that I would probably draw, probably not with this much detail, but I would certainly draw it on my test booklet as I was just trying to keep track of what was happening in our equation. So we have 1.25 molar HCl. We have 29.95 milliliters of the acid. We were told up in the problem originally that we had 45 milliliters of stock solution down in our Erlenmeyer flask down there. And so we're asked to calculate what is the concentration of KC6H7O2, potassium sorbate. What is the concentration of that solution from here? So what we know the volume of the solution down there. We know we have 45 milliliters, but we don't know how many moles are there. And what we're going to be able to do is understand that in a titration, when we get to the end point or the equivalence point right here, we're going to be able to see, get a stoichiometric relationship between our two reactants. Okay, and so if we know how many reactants or how many moles of hydrochloric acid we have, we can then use stoichiometry to compare how many moles of sorbate we had, and then get our concentration. Okay, so the calculations are pretty straightforward because we're just looking at the molarity equation in two different forms. So we know that molarity is equal to moles over volume. So we're going to rearrange that to say moles is equal to molarity times volume. We fill in our numbers here. Be careful, we've got 29.95 milliliters. That's a tricky one for a lot of students to convert into liters, right? So we're going to move, you might want to divide by 1,000. You might want to move the decimal point over 3 places. In either way, we're going to end up with 0.0375 moles of HCl. And because in our net ionic equation, which is balanced, our moles of protons are equal to the moles of sorbate, they're in a 1-to-1 ratio, we can assume that our moles of sorbate is equal to moles of HCl. And then we just can plug those into our molarity equation. Molarity is equal to moles over volume. And we're going to bring this number down. We've converted our milliliters into liters again, and we should get to a concentration that is 0.832 moles per liter. Okay, and so that's our final answer for part B. What I've done here for part C is I've given you two different student responses. So these are our actual students wrote these words out in order to justify their answer. I'm going to give you a second to read what student 1 said. They're justifying why thymol blue, they believe thymol blue is the best indicator. And student 2 believes that bromothymol blue is the best answer. So read through their justifications and also read through, just compare their solution to your solution. What we're identifying is that at the equivalence point, the pH is measured to be 2.54. So we want to know which of the following indicators would be the best choice for determining the endpoint of the titration. We're given 5 of them here. And I hope that you're able to identify that student 1 was indeed correct here, that thymol blue is the best indicator for determining the endpoint of the titration because the indicator changes color when the pH is equal to its pKa. So the thymol blue has a pKa right here at 2.54. Of course, they're not exact. We're going to look at a graph of this whole situation in a couple of minutes, and we'll see why the fact that they're not exactly the same is probably going to be okay for this. If we had a different indicator that was closer, changed color closer to 2.54, then that would be great. But what we're looking for is a pKa that is close to the pH at the endpoint. That's when the color change would be happening, and that is what identifies a good indicator for us to use. Okay, what's interesting over here is a lot of students will think that, like student 2, that if we just put a whole lot of information in there, we just keep talking, that more information is always better. In this case, I thought this was a good example of student 1 knew what the right answer was. They told us what the right answer was. They kept their justification short and sweet, and then moved on to another problem. So don't feel like you need to go on and on and on about what you're to justify your answer. If you're able to give a clear and succinct answer, that's always the best way to go about it. Let's look at two different student answers for part D. Compare this work to the work that I hope that you have already done. We're trying to calculate the pH at the half equivalence point. Student 1 said that at half equivalence, the concentration of base is equal to the concentration of the acid. So the pH is equal to the pKa. and then just plug the pKa into, P of anything is the negative log of, so just calculate it or plugged it in over there. And student 2 said that at the half equivalence point, also understood that the pH is equal to the pKa, but said that the pH must be equal to 7. So which do you think is the better answer here? And it turns out, I hope you're able to identify that student 1 is correct again. I'm not sure if this is the exact same student 1, but student 1 was able to identify that the pH is equal to the pKa, and that then involves a calculation here, right? So student 2 just forgot to do the calculation or assumed that the pH was going to be equal to 7, made sort of a strange assumption there. This calculation in here is something that I think many of us are familiar with. We've talked about this relationship here multiple times throughout our lessons. Here with Mr. Faribault. I believe I can remember a lecture where he was talking specific, or a lesson he was talking specific about that. So we'll go back and look at that. Okay. Problem or letter E asks us to do some drawing, accurately sketch the titration curve on the graph below, mark the position of the half equivalence point on the curve with an X. So we definitely want to make sure that's kind of actually a really nice hint for us in terms of how we would solve this problem. And if it were me, I would want to start with that half equivalence point on the curve with an X first, and then sketch the rest of the curve in there, right? Because 2 points right here, if we just drew a straight line, I suppose is one way a student might go about this. So you see 2 points and you just try to connect them. But certainly when we fill in the equivalence point, we would see, or the half equivalence point, we would understand that we are not looking for a straight line here. Okay, and so what I would say is I probably want to identify from part B that the volume at the equivalence point was 29.95. So if I go back and I read the problem at part B of the problem, we see that the equivalence point had a volume at 29.95, and that should be consistent with the pH that's here as well. So we didn't have to do this drawing, but just remind ourselves where we were at. We need this number because we have to get to halfway to the equivalence point, right? So if the equivalence point was 29.95, what we're going to say is the volume at half to the equivalence point is just shy of 15. In part C, we calculated what the pH at the equivalence point is at 4.8. And so we're going to put an X right about right there. Now this is a sketch where we don't have a whole lot of lines there to get super specific, but forgive me if my estimation is not exactly where you would put it, but certainly less than 15, right? If this is 10 and this is 20, here's 15. So we want to have the X be a little bit less than 15 and just below the pH of 5. So once we have our 3 points here, okay, we certainly, again, we don't want to have a straight line. We want to have a titration curve, and there are 3 parts of this curve that we want to be careful about. So I would sketch it into be something similar to this. And what I'm looking for is a halfway point that is consistent with whatever my answer was previously. So the scoring guidelines say you may have gotten part C wrong earlier on in this problem, but as long as your curve is consistent with that, you're going to get the point for this for being able to sketch the curve. Okay, so we would never get you double dinged for making a mistake here. So this is consistent with our answer that we had before. We want to make sure that we have a relatively horizontal line at the halfway point, or halfway to the equivalence point, okay? And that's because we're in that buffer zone. I think one of the students mentioned a buffer zone. So we see that there's going to be, we have a concentration of both the acid and its conjugate base. And so because we have both of them there, we want to, there's going to be a relatively flat titration curve, which is indicative of slow change in any kind of a pH, right? But then once we get close to the equivalence point, the pH is going to change really quickly. And so we want to have a steep slope here. And this is where we see that because there's such a steep slope here, that indicator that was going to change at 2, there's not going to be a very large change in the volume that we've added. We're going to have a pretty quick change in pH with very small volumes. And so using that indicator that changes at a pH of 2 would be just fine. Okay, so 3 points or 3 aspects of this graph that the scoring guidelines were looking for: a value that was halfway, that's consistent with what you had your answer before, that you have a flat curve right here, and that you have a steeper slope near the equivalence point. Okay. Last part of the problem, let's look at student 1 and student 2 again. This question is asking us which species the acid or conjugate base has a higher concentration in the soft drink when the pH is 3.37. Student 1 is going to say that the acid has a higher concentration because this is an acid and that's a base, and the pH of the soft drink is acidic. And because it's a weak acid, it will barely dissociate to form the conjugate base. And then student 2 says, since the pH is 3.37, the species of the acid is a higher concentration because the pH is acidic and this is an acid. So I tricked you here because neither student 1 nor student 2 really had a good answer here, okay? What we're gonna want to identify is really what student 3 said. If the pH is equal to 3.37, we're way past the halfway point, okay? So we can look at, we can think about what happens at the halfway point. We know that our concentrations of the acid and its conjugate are equal to one another. And so since the pH is lower, there's more acid that is present. So this is, when I looked at the student's response, I thought they had done a really nice job of graphing, of creating a sketch of their titration curve. And so then they were using that to their advantage to see which species was present. Which was more present. So we saw in student 1 and student 2 is that they gave us the correct answer, but they did not have good justification for why the answer was acid, and so they may have received one of the 2 points, but wouldn't have gotten full credit for it. Student 4, so I have another solution that I thought was really cool, the way that this student had answered the question. So I just wanted to show this to you. Maybe this is just my mathematical brain. But this student went back to the equilibrium expression, the Ka for this reaction, and said that we can set up what the equilibrium expression would look like. Ka is equal to the concentration of the ions over the concentration of the acid. Because this is a weak acid, we would have all 3 of these present at the same time. And really what this question is asking for is a ratio between the acid and the conjugate base. And so this student rearranged this expression up here to just say that the ratio of conjugate base to acid is equal to the Ka over the concentration of protons. And because we have both of these values, 1.7 times 10 to the minus 5th is given to us as the Ka earlier on in the problem. We know the pH, and so if from the pH we can calculate what the proton concentration is, we can calculate out this number and we get 0.04 as our answer. And because an answer of 1 would tell us that this ratio is a 1-to-1 ratio, and as this number gets lower than 1 or closer to 0, less than 1 and closer to 0, we know that the concentration of the conjugate base goes down, the concentration of the acid goes up. And so our conclusion here is that our concentration of the acid is much more than our concentration of the conjugate base. So I thought that was just a really nice example of using some relatively simple, straightforward mathematical principles, using some definitions that we have from multiple different pieces of our chemistry experience to get to a mathematical understanding that makes complete sense. So whether you're able to spell that out with a couple of bullet points or whether you're able to solve this mathematically, you would get to the same solution, which is that there is more acid present than conjugate base. Okay, so that is all of our first problem. Given the fact that that was a number of different steps, seems to model what a question number 1 or a 25-minute question would be for you. Now I'm going to give you 2 different 15-minute questions. We'll do them one at a time. So I'm going to give you one, show you your solution, and then show you another one. So here is a second question for you today. I think the SOTA model is what we would do in question number 2. I would expect you to be able to answer this in 15 minutes. Apologize that the font is so small, but take a screenshot of this or just pause the video where it is right now, and we'll come back with the solution in a couple minutes. Okay, so I'm assuming that you have already paused the video and you have a solution to this problem sitting in front of you that should have 3 different answers to it. The first one is, the first question asks us that the metal one is in excess. And so we want to calculate the number of moles of iodine that has reacted. So as I was looking for a solution to this problem, there's a couple of key pieces of information that I am going to want to zoom in on, okay? So the one way to look at this is that we see where iodine was added, and between the masses, if we know the masses of the beaker before iodine was added and after iodine was added, we know the mass of iodine that was added, and we can then convert that into moles. That information is also found down here. It's exactly the same information, so wherever you got the data from, you would have come to the same conclusion, right? So I'm going to say that the grams of iodine that reacted were 127.570 minus 126.549. I got those right off of either our balance up here or off of our data table down here. But either way, I get 1.021 grams of iodine that are present. Then I would have to look on the periodic table, and I would see that the molar mass for iodine is 1.2 or 126.90. And I'd have to be really careful here that to make sure that I use I2, okay, the diatomic molecule iodine. Its molar mass means it would have twice the twice or 2 times 126.90. So that's where this 253.80 grams comes in. And so our solution is that 1.021 grams times 1 over 253 gives us 0.00423 moles of I2. Okay, so really just reading the information that's here. The problem with this, when I look at this problem, there's so much information that's thrown at us here. We really have to zero in on what is the essential information for us to know, for us to be able to use in order to solve the questions that's there, right? So how do I know what? I just have to take a minute to make sure that I'm only looking at iodine, and that's why I drew these red lines around here. Okay, part B asks us to calculate the molar mass of the unknown metal. Well, what's the definition of molar mass? Molar mass is grams per mole. So I'm going to have to look at my equation up there. So M, whatever the unknown metal is, plus I2 produces Mi2. And I'm going to want to use that in order to figure out, or to reinforce for myself, that the moles of M are equal to the moles of I2. They are together in a 1-to-1 ratio. Okay, so if our equation tells us, if this is a balanced equation, and it's represented by the equation above it, we'll reinforce that from the problem that's right there. So I can assume that the moles that I calculated in part A are equal to the moles that I calculated in part B, or the moles that I need in part B, so that'll be the moles of M. And now I just need to use our mass down here. So there's our mass after the second weighing. It turns out that it's the mass after the first weighing as well. So we know that all of the water was evaporated. I'm going to calculate what was the mass of M that was left over, right? It was that was used in the equation. Okay, so the moles that were used and the mass that was used, we had a whole excess leftover mass that was right here. So we can't just use all of the mass of M that was added up here. We have to get moles and grams in an equal ratio to one another. And so we're gonna, the only way to get rid of the leftover M is by using this mass of Mi2 down here, subtract out the iodine that's as a part of this, and that gets us just to the mass of the metal M. And then we can just go to molar mass. Is our definition is grams over moles. So that's our moles from the earlier problem. our grams that we just calculated right here, and we end up with a molar mass of 65.4 grams per mole. Lastly, I'm going to show you two different student responses for how they proposed an experiment to test whether this was an ionic compound or not. Okay, the first one student suggested that we dissolve the compound in water and then test if the solution conducts electricity. Now, what's nice about this student's solution or response is they not only said we should test it for electricity, they also explained how the results of the test would support the hypothesis, right? So it's not just this is an experiment I can do. This is suggesting how you would interpret the results of that experiment in order to confirm or reject your hypothesis up here. So the student goes on to say, if the compound melts and the solution conducts electricity, there are mobile ions capable of carrying a charge, so the compound is likely to be ionic. I'm sure many of you have done experiments like this in class where you have tested the conductivity of a solution in order to determine if it is we typically use the word electrolyte. I just grabbed this graphic for you just to remind yourself that we can have some solutions that will dissolve in water. Ethanol would be a great example of ethanol. Will dissolve in water, but because there are no ions created, it will not conduct electricity, right? Whereas potassium chloride, which is a very classic ionic compound, even though it has a different chemical formula, its ratio is just 1:1 here as compared to up here we have 1:2 ratio. We still have free ions. They're able to flow through the solution, and so they would conduct electricity. And the last thing we know is that the conductivity of electrolyte is related to the strength of the electrolyte. So if there are more ions in here, it will conduct electricity better. If there are fewer ions, there would be less conductivity. So what we see here is lots of ions in this beaker. So we have a bright light and fewer ions here. So we have a dimmer light bulb because there's acetic acid, right? A nice weak acid, similar to the weak acid we talked about in the first problem. Now we could do a similar experiment where we just melted the salt, we melted the compound in order to see if it conducts electricity. Typically, a high school doesn't have, and maybe even some colleges don't have the capability of melting a solid crystal structure and then conduct electricity without melting whatever the apparatus was to test the conductivity as well. And so that would be an acceptable answer here. You could melt to the solution, and one of the characteristics of an ionic compound is that it's liquid form. So it's not dissolved. It's liquid formed where we melted the salt does conduct electricity. I don't have a picture of that for you because it's not an experiment that many of us do in our classrooms or that you may have seen. And this is a much more typical one. And so this would be a great example of a problem that you would want to show. The second acceptable answer was to talk about the melting point, but just to talk about the relative value of the melting point. We know that ionic compounds tend to have high melting points. And so if you test the melting point of this compound and you find it to have a high melting point, it is likely to be ionic. This was an acceptable answer. Both of the solutions I've showed you here were acceptable answers in the scoring notes, as well as melting it and then testing its conductivity. So any of those three things that you wanted to say would be good to go, okay? Our last problem for today, I think, is another 15-minuter. We've got about just 3 questions here. We're looking at the solubility of calcium hydroxide. So take a minute to pause your video here, answer these 3 questions, and then come back to me when you're ready. Okay, I'm going to assume that you have at least some sort of a solution in front of you as we tackle this problem. First thing we're going to do is write a balanced chemical equation for the dissolution of calcium hydroxide in pure water. I hope that this is a relatively straightforward one for you. We're just identifying that calcium and hydroxide are the 2 ions, that we would have 2 OH minuses that are here. We would identify calcium hydroxide as a solid, okay, as it's listed here, but then both of these would be aqueous. Okay, so a really essential part of solving the rest of this problem is being able to show this equation. So a good place to start. Then to calculate the molar solubility, we're going to have to do either an ice table. What I like to say is that I'm going to ice it down. I can hear my students rolling their eyes at me when I say that every time. Mr. Faribault talked about a rice table where we have a reaction and then the initial concentrations, what's the change, and then what does this look like at equilibrium. Remember that we define molar solubility as the maximum amount of calcium hydroxide that can dissolve in a solution before we make a precipitate. So it's imagining we can exactly get to a certain amount of calcium hydroxide that dissolves, and we have absolutely no precipitate, but if we added just one more molecule in it, that molecule would cause precipitation. Okay, so we're looking for a concentration of calcium hydroxide. Okay, and what's interesting about the problem B here is that we're also dealing with a common ion. So we're going to look at calcium nitrate here and see that nitrate is just going to be a spectator ion. It doesn't really do anything for us, but the solution already has some calcium ions in it. And because the calcium to calcium nitrate ratio is 1:1, we can assume that the concentration of calcium in our solution before we even add any calcium hydroxide is 0.10. Okay, now be careful if for some reason we had a different ion here, we may want to be thinking about the nitrates, and then we would have to double this. We might have a 0.2 as we would put into our ice table. So that would be a way that we would make this problem even trickier. But for this one, just answering what's here, calcium is a 0.1. We know that every time we add 1 mole of calcium, we add 2 moles of hydroxide, right? So plus X, and we're going to add plus 2X over here, so that at equilibrium, we have 0.1 plus X, and we have 2X for our OHs over there. Right, so this is a little bit more complicated of an ice table than we've had before, but that's because of our ice table, or because of our common ion, excuse me. And so we're recognizing that the 0.1 is brought down into here for the common ion. Okay, it's a little more complicated also because we don't have a 1:1 ratio here. We have 2, so we have to make sure we bring down a 2X. If you go back to our lesson on solubility problems from Mr. Faribault, we're going to remember the math is about to get complicated as well. So I'm going to really go slowly through these steps for you so you make sure that we get this one right. Our KSP expression is calcium ions times the concentration of OH squared. That's the definition of a KSP expression. And we're told that the value is 1.3 times 10 to the minus 6. Now remember that because we have in the net ionic equation, the calcium hydroxide itself is a solid, it does not get included, right? It's a different species. We would call this a heterogeneous mixture. So the solids do not get included, only the ions that are in solution get included here. And remember that this 2 here is here because of the coefficient on the balanced net ionic equation. Okay, so there may be a 1 that's our exponent up here, but we have a 2 up here because of our coefficient on hydroxide. And then we're going to just fill in or plug in our equilibrium concentrations from our ice table earlier on. Okay, and so many students are going to get confused on 2 different things here. First, they're going to forget to put the 0.1 minus X. They're either just going to put the 0.1 or just the X. We'll talk about that in a minute. But they'll forget to put the 2X and the squared here. Remember that one of them has to do with the stoichiometry. The 2X has to do with stoichiometry, and the exponent of a 2 here has to do with the equilibrium expression with the KSP. And so both of them need to be present here. Skipped ahead too quickly. All right, so take a second just to make sure that you're comfortable with how I filled that in. I'm putting together, so this first line up here, I got the KSP expression from our net ionic equation. I filled in my values from my ice table. Okay, and now it's just algebra, but again, this algebra is a little bit tricky. Okay, so you're going to see that I simplify the 1.0, I'm sorry, the 0.10 minus X to just 0.10 because we assume that X is way smaller than 0.10. So we can assume that this X is not consequential. Now, if you had all the time in the world and a graphing calculator, we certainly could solve this, leaving that in. And if you want to go ahead and do that, you're going to see that you will get to the same answer. And so it's completely acceptable on the AP test just to make this assumption. Sometimes we call this the small x rule, but we would probably just want to write a little note here that the assumption is that x is much less than 0.1. And then remember that this exponent of a 2 gets distributed over both the 2 and the x, and so 2x quantity squared turns into 4x squared. Okay, so this step is another spot where students will oftentimes make a mistake. We can then, I'm going to go through the steps of simplifying it. So 0.1 times 4 is 0.4, and then our x is equal to our 1.3 times 10 to the minus 6 divided by 0.4, and then we'll take the square root of that whole thing, and we'll get 1.8 times 10 to the minus third as our concentration, or as our solubility. And because X is the concentration of calcium, and it's the concentration of calcium hydroxide, we can say that this is our molar solubility of calcium hydroxide. Okay, so this is a good problem for you to run through a couple of times and just be really careful with this math. This is an example of multiple things all happening at once that you're really just, as soon as you solve a couple of these, you'll feel really comfortable with them, but there's a high margin of error in theirs. Last one is doing some drawing again, drawing some maybe particle representations here, particle pictures. We want to draw 4 water molecules in the correct orientation around calcium. They give you a suggestion for what those water molecules could look like. Okay, I'm going to blow this up just to make sure that we are clear on what parts are what in this water molecule. And so in my mind, I may sketch this out on the side of my booklet, or just have this in my mind as is my thinking process before I answer the question. Remember that the oxygen is really that atom that's in the middle, and the hydrogens are on the outside. So this suggests that bent shape that we typically find for water. I might even fill in some lone pairs of electrons out here. But what I really want to clarify is that the slightly positive side of the ion is the top part, is closer to these hydrogens, and the slightly negative side, this delta, typically means slightly positive or slightly negative. By that we mean that oxygen, being a little bit more electronegative, is going to pull on electrons a little bit more strongly than the hydrogen. So we have a little bit higher electron density on the bottom side of the molecule as it's drawn, or closer to the oxygen. This has a slightly negative charge, and so what that means is that the slightly negative charge will be attracted to the full-on positive charge of the calcium ions over here. And so if we transfer one of the molecules, just as it's written there, over to our calcium, we would do it in such a way that the slightly negative side is closer to the positive ion. And now the question asks us to do 4 molecules. So we're going to want to put all 4 around the outside. And in all 4, we want to make sure that the orientation of our water molecule shows that the oxygen side, or the slightly negative side, is closer to the calcium, the Ca2+. And so this would be the acceptable answer. What's in the box is the answer. This slightly blown up drawing over here is just for your sake, to make sure you understand why I would get to that answer. Okay. So that brings us to the end of our lesson today. There's 3 different free response questions to think about, a longer one and 2 shorter ones. Get in the practice of doing these, maybe with a timer on as you're going through it. Mr. Faribault will be going through some more problems with us next week with a timer up on the screen. So that will be a little bit, again, another step in your process of closer getting prepared for that test on on May 14th, right? Keep going back to apcentral.collegeboard.org with any questions that you need. We put a bunch of links down below, so check those out when you have them, when you have a second. If you haven't looked at watched our video and our interview, our conversation with Dr. Arnold, go back and look at that right away. Enjoy your day. Thanks for watching, and we look forward to seeing you soon. Have a great day. Bye-bye.